In this lesson, we are going to learn more about mixtures, types of mixtures, and how to classify matter, and then to represent all that matter in particle diagrams. So we're going to start with this flow chart. And in this flow chart, it starts at the top. We are talking about classifying matter. Right? Matter. Matter is a very generic term. Question to ask yourself is, can the matter be separated by physical means? By using a physical property such as size, color, texture, mass, weight, or density? If you can separate it by physical means, we would classify that matter as a mixture. And if you cannot separate that matter by physical means, we would classify that type of matter as what is called a pure substance. And we're going to start on this side because we've already talked about pure substances, whether or not you recognized that's what we were talking about. Because if you have a pure substance, if it can be chemically decomposed, broken into its parts by breaking chemical bonds, if it can be chemically decomposed, we are talking about a pure substance, which is called a compound. If you cannot chemically decompose that pure substance, it is an element. Now, let's try to capture what a compound looks like in a particle diagram. There's all different kinds of compounds, but for simplicity's sake, let's draw a simple binary compound. Binary compound, of course, means only two different kinds of elements. So I'm going to draw an atom that I'm going to shade in, and I'm going to show two other atoms as white circles chemically attached to that circle in the middle. Okay, so let's draw a couple of those. And I'm going to draw them definitely kind of as randomly associated with each other as possible. We could fill up this whole thing, but we're just going to leave it like that. So a compound, the smallest particle that we are looking at here is referred to as a molecule. But collectively, we would refer to this as a compound because we have these particles where there are at least two different types of atoms chemically connected. An element can be portrayed one of two ways. So I'm going to show two particle diagrams here. Elements are portrayed typically just by atoms, right? So this circle right here is an atom. And most elements have this form. Most elements are made up of atoms. There are 7 elements, however, that are diatomic. So let me go back here. So this type of element that's made up of atoms, these are called monatomic elements because they are made up of one atom particles. We also have diatomic elements, and they are consist of particles that have 2 atoms of the same type. So we might draw that something like this, as 2 circles chemically connected. Okay. So diatomic elements, their smallest particle is a molecule. Remember, so a molecule is any type of particle where you have at least 2 atoms chemically connected. In the case of this diatomic element, both of these atoms are identical. In the case of a compound, there are 2 different elements connected. There are only 7 elements that do this diatomic thing, as you recall, with the acronym, the Brinkel-Hoff. Those elements exist diatomically as Br2, I2, N2, Cl2, H2, O2, and F2. And those are not all together. Those are just the 7 different elements, how you would write their formulas. So pure substances are a type of matter that are classified as either compounds or elements depending on whether or not they can be chemically decomposed. If the matter can be separated by physical means, we are looking at mixtures, and there are 2 types of mixtures that are dependent on how uniformly they are mixed. If they are uniformly mixed, we refer to it as homogeneous. If they are not uniformly mixed, we refer to them as heterogeneous. Okay. Let's try to draw this as a particle diagram. I'm going to draw a series of two elements, both monatomic elements. And so I'm going to start by drawing one of those elements as a series of, I don't know, 6 or 7 or maybe 8 of these atoms, just sort of randomly spread out as randomly and as uniformly as possible. And now that's one type of element, right? That's one type. And I'm going to draw a second element as just plain open circles. And I'm going to try to draw them interspersed like so. Okay, so that's pretty as evenly as possible. Those two different monoatomic elements are mixed together. They are not chemically joined. You do not want to draw those close together, because if they were joined, we would be showing it as a compound. And we're trying to show this as a homogeneous mixture of two monoatomic elements. Okay. There's other pictures that we could draw, but this is the idea we're trying to convey here, is that the particles in this mixture are evenly distributed amongst each other. For heterogeneous, we're going to draw it a little bit differently. And let's say we have, we're going to draw a monoatomic element. They're not touching, right? But they are close together, and they are, what do I want to say? They're orderly. So this might be a picture of a monoatomic element in the solid form. Solid particles are arranged in a regular repeating pattern. They're relatively close together, and they hold their shape, right? So this is, so far I have not drawn a mixture. I've just drawn an element in the solid form. So if it's a mixture, I have to bring in a different type of particle. And for this, I am going to draw a diatomic element, and I'm going to have this diatomic element, I'm going to show us a series of these particles kind of randomly arranged around. Okay. The idea here is that it's pretty obvious that I have one area that is very differently mixed than the other area. So this heterogeneous mixture is not the same throughout. All right, so let's talk a little bit more about this. Let's go to the next page. We have a definition up here that says mixtures. Mixtures have components that can be separated into their component parts based on differences in their physical properties of the different components. We'll be getting to that concept, what physical properties we can use to separate them. That's going to come a little bit later in the next lesson. This lesson, we're still trying to focus on the mixture types and the particle diagrams and how to represent mixtures in particle diagrams. So here we have a homogeneous mixture. You can see that there are some of these particles which are a little darker than the others, and so there's these little dark particles that are fairly evenly spread out. Here you can see that there's a clump of one type of substance, very different and ununiformly mixed from the rest of it. Okay, so homogeneous, is it a constant composition throughout? Yes. It's evenly mixed. And what's crazy is, if we're looking at a particle diagram, you would never see the particle diagram. That's just our two-dimensional modeling. We're going to be talking in a moment about what a homogeneous mixture looks like on a normal everyday scale. We'll come back to this box in a minute. So homogeneous, yes, is constant composition. It is evenly mixed. Heterogeneous, no, it is unevenly mixed. Okay, we're leaving space because we're going to come back to that in a second. In a homogeneous mixture, will these particles settle out? The answer is no. This type of mixture stays mixed. A heterogeneous mixture the particles, these big particles, will settle out because they tend to be big and heavy and more dense than the surrounding liquid. So the answer here is yes, if that heterogeneous mixture is an aqueous mixture. Remember, aqueous means dissolved in water, right? So if this lighter molecule here is water and these are something else that's mixed in the water, but unevenly, those particles are pretty big and they're going to settle out. Okay. So let's take a look at some generic examples. This idea of this heterogeneous mixture settling out is what we call a suspension. Okay, that's the term for it. These are things that need to be, you have to shake these. You have to shake it to mix it up. Okay, and you might think of like Italian salad dressing has to be shaken before you use it. Not Alka-Seltzer. Pepto-Bismol has to be shaken. It's a medicine for indigestion. You have to shake that up before you can drink it. Orange juice, the kind that has pulp in it, you have to shake it for the pulp to get mixed throughout. But eventually the pulp is going to settle. Okay. A homogeneous mixture is typically referred to as a solution. So when you hear the word solution in this class, you know that you are talking about a homogeneous mixture. In a solution, you have something that is called a solute, right? This is, for example, if you, not that you would ever really be making this, but if you were making salt water, the solute might be something like the salt that you're adding. You're going to add that to the solvent, which might be water, and that's going to turn into a solution, which is, of course, the salt water. Okay, so the solute is the stuff that you're dissolving into the medium that you're trying to put the solute into, right? So once you make that salt water, that salt stays dissolved. The salt does not settle out. Specific common examples of solutions. Kool-Aid, when you mix up the Kool-Aid powder into the water, right? The Kool-Aid powder dissolves into the water and it doesn't settle out unless you've added too much. If you've added too much, then there might be some left over. But if you can dissolve it, it stays in the water and it does not settle. Okay. Tap water is a homogeneous mixture. Tap water is not pure water. It's got stuff dissolved in it because water comes out of the ground and there's just natural minerals that are in the water. Homogenized milk. Homogenized milk is called homogenized because the processing of the milk causes the little fat droplets to stay suspended and they won't settle out. They stay mixed in the milk. Steel is a homogeneous mixture of carbon and iron. Coffee, right? Coffee is a homogeneous mixture of the coffee molecules mixed in with the water molecules. All of those things stay dissolved in, and we consider those to be solutions, which means they are homogeneous mixtures. Examples of suspensions or heterogeneous mixtures are, we mentioned it earlier, salad dressing, specifically Italian, when you have the vinegar and oil. You have to shake it up to make it stay as mixed as possible. Fresh milk, when it comes right out of the cow, right? If you have fresh milk and you let it sit, the cream will rise to the top. It is not naturally a solution. It will separate out. A salad with the greens and the tomatoes and the cucumbers and whatever else you put on your salad is a heterogeneous mixture. Every bite of salad is likely to be a little bit different. Another example is blood. Blood looks like it might have all the substances dissolved in it, but if you can take a blood sample and run it through a centrifuge, forcing the cells and the platelets and the other particles that your blood is transporting will settle out to the bottom of that sample. Soil is another example of heterogeneous mixture, all kinds of things mixed unevenly into the soil. And iced drinks, right? Even if the drink itself looks completely blended, the ice makes it a heterogeneous mixture. All right, let's take a look at the third page. This is meant to help us kind of practice together and to classify particle diagrams based on what we have been learning so far. Okay. Particle diagrams, as you've been seeing, are two-dimensional representations of the particles of a substance. Okay, there's that word particles. Particles are either atoms or they are molecules. Right, so think of the word particles as more of a generic example, and atoms and molecules are specific examples of particles. So here is a particle diagram. The first thing I'm asking you to do is to check the box as to whether this is a homogeneous mixture or a heterogeneous mixture. Okay, I'm looking at this and I'm seeing that things are fairly evenly mixed. I would classify this as a homogeneous mixture. The second one, I would look at this and say this is pretty, all these particles, this particular particle, they're all intermingled. I don't really see one area that's different than the other. I would classify this as homogeneous. Okay. This right here maybe looks like it's not a mixture, but if you look carefully, this is a slightly different type of particle than this particle. And again, as best as we can tell, this is fairly evenly mixed. Okay. I would even say, so the first four, I would say are homogeneous mixtures. Now let's take a look at the next section. Here I have a distinct separation between this type of particle and this type of particle. I'm going to classify that as heterogeneous. Again, look at here, I've got different sections that are quite different. Heterogeneous. I've got two different particles. Again, layers. If you see layers of particles, definitely heterogeneous. Layers, heterogeneous. Again, layers of two different particles, heterogeneous. All right, so that kind of gives you an idea of how you would classify homogeneous distinctly from heterogeneous mixtures. Let's go back and take a look at each one of these and decide if we have gas phase, liquid phase, and or solid phase. What we have here is regular arrangement, very ordered. I would classify this as solid. If you see particles floating up and filling the entire space of the box, I would classify that as gas phase. The next example, we have particles filling the space. I would again classify that as gas. I would classify this next one as a gas. This is a little less obvious because we have some blank spaces, but again, this doesn't, if this were a liquid, gravity would have this layer down at the bottom. So I'm gonna argue that this one is meant to display gas phase. All right, here, what I would say is we have two different substances, both in the solid phase. I'm gonna skip this one and we'll come back to it. For this one, I would venture that we have here, we have a liquid because they're close together, but they're at the bottom. So I'm going to say that this is liquid phase, but up here, because the particles are filling that space, I would say that we have a gas phase too. We have both there. Okay. For this one, I'm thinking that this is probably, you could argue this either way. I could say, I could almost, tough, this is tricky. I could argue this to be a liquid phase and this to be a liquid phase. This one's definitely kind of tricky. This one's filling up the space. So I'm going to venture that this down here is liquid and that this is gas. So I'm going to say we have liquid and gas here as well. So coming up to this one I think is tricky too. We definitely have layers. You could argue that these are a layer of a liquid and a liquid. But they're not super random. Like all the molecules are oriented the same way, which lends me to believe that this is a solid, but they're also not orderly and packed like really in an ordered situation. So I'm going to say that we have 2 layers of liquids on this one. Okay, there definitely can be a little bit hard to interpret, but we're going to do our best to reason our way through those choices. Lastly, what we're going to do is we're going to look at this particle diagram and we're going to decide what we have in this particle diagram. Do we have an element? And if so, is it monatomic or is it diatomic? Do we have a compound? And if so, is it binary or ternary? I'm going to argue that because these are all packed together tightly, that this is one type of element and this is another type of element. So I would argue that this is a monatomic element and this is a monatomic element. They're just packed together super ordered and super evenly. So I'm going to say that there's 2 elements that are both monatomic. In this one, I would say what we have here is your element that is monoatomic. And I would say that this one is an element which is diatomic. I know it's an element because they are both the same shape and shading. So I would say that that is a diatomic element. Okay, we have 2 different particles here. This is a compound. We know it's a compound because we have 2 different shapes. This is a compound because there's 2 different shapes, or 2 different shadings anyway. The question is, are these binary or ternary? Binary means there's 2 different types of atoms, so I would classify this as binary compound. This is also a binary compound because even though there's 3 atoms, there's only 2 types of atoms. So in this case, we have 2 types of binary compounds. In this next diagram, we have a monoatomic element here and a different monoatomic element here. I'm going to say, check that box, but we have 2 different kinds of monoatomic elements. In this example, I've got a diatomic element here, and here I've got a different diatomic element. So I'm going to check element diatomic, and I'm going to write the number 2 because we have 2 different types of diatomic elements. Okay. This is a element, monoatomic. It's just, they're packed together in the solid form, but these are just single atoms packed together. So this is an element, a monoatomic element. This is a different kind of monoatomic element. So I'm going to check that element monoatomic, and I'm going to put 2 after it because we have 2 different types of monoatomic elements there. All right, in this one I have a diatomic element here. Check that box. Here we have a compound, right? It's 2 different kinds of atoms there. So this is a compound. And it is binary because there is 2 different kinds of atoms that are present. All right, 2 more to classify. In this box, monoatomic element, diatomic element. And lastly, once again, monoatomic element, diatomic element. All right, there is 1 more page of the notes, but we are going to come back to that in a separate lesson. So for right now, you have completed section A and section B of the section unit 0.4 notes on mixtures, where we classified matter into mixtures or pure substances. We then got looking at particle diagrams of mixtures, and we tried to classify those particle diagrams as homogeneous or heterogeneous mixtures, classify them as state of matter that they're in, and then what kind of substances we have present in those particle diagrams. All right, let's try the problem set in class, and I'll see you back in the classroom.